Hello and welcome everyone to our calculus notes on extrema on an interval. So first off, the definition of extrema. It says let f be defined on an interval I containing the point x value of c. So f of c is the minimum of f on I if f of c is less than or equal to all f of x for all x in our interval. Okay. Likewise, f of c is the maximum of f on I if f of c is greater than or equal to f of x for all x in I. So what this is saying is, if we look at a function, okay, and we put this on an interval, say from here to here. Okay, so there's our interval I, and let's just look at this point right here. This would be our minimum value because f of c right here would be lower than all of other values of f of x. So we're going to call this a minimum here. And we think of this like a valley. So any valley is going to be considered our minimum. Now on this interval, we also have the highest point, and we're going to call that our maximum. And we think of this like a hill. Okay, so you can see on this interval that this value is higher than any other, and on the interval this value is lower than any other ones. So we call these extreme values, or extrema, and the minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum on that interval. So if we just look at that interval, absolutely, this is the minimum. Okay. Now extrema that occur at endpoints are called endpoint extrema. So let's take a look at three examples. We all have the function x squared plus 1, and we're all going to be on the interval -1 to 2. Now this one is actually on a closed interval because of the square brackets right here. Okay, so square brackets mean closed, and it means that we're going to include the endpoints. Okay, so we're going to include the endpoints here. So first at -1 and at 2, that's our interval. And so we're just going to plug in our values here. -1 squared plus 1, that equals 2. And then 2 squared plus 1, that equals 5. And those are going to be closed circles right there. And we're just going to add the point at x equals 0. So 0 squared plus 1 is 1. And because this is a parabola, we're going to draw this just like this. So in looking at this, the minimum is going to be the lowest value, so that's right here. And the maximum is going to be right here at this value. Okay, so we have our min and our max. Now in this next example, now we only have parentheses around our interval. We call this an open interval. And so we don't include the endpoints. Okay, so don't include your endpoints. We still use them as our interval though. And so what happens is now we get an open circle there and an open circle here. And the function didn't change. Okay, so the way this works out now, the minimum value is right here. Now we come back over here where we had a maximum as an endpoint extrema right here. But on an open interval, that endpoint doesn't actually exist. So the function never actually reaches that point. So what is the highest value? Well, because we don't actually have a highest value, we say this is there is no maximum on this interval. Okay? So it's kind of strange there. Let's look at our next one. Here, the function x squared plus 1 is good everywhere x does not equal 0, but when x equals 0, our function equals 2. And we are going to be on our closed interval. So at -1 and 2. So closed interval now, we are going to get our points here. And we know that when x equals 0, y equals 2. So the parabola still looks the same, except now we're going to have a removable discontinuity right there at 0. Okay, so let's find our maxes and mins. So the same type of idea is applying. We don't have a lowest value here, so we actually have no minimum. But now because our maximum is an actual value, our maximum is right here. So we're going to look at this now through the lens of the extreme value theorem. So we say if f is continuous on a closed interval, then we know that f has both a minimum and a maximum on the interval. Okay, so let's take a look if that holds true. So our first one right here is continuous, and it's also on a closed interval. And what do you notice? We had a max and a min. And so we're going to be guaranteed a max and a min when both these things are true. Okay, so let's look at our second one. Our second one was also continuous, but it was on an open interval. So because it was not closed, a max and a min are not guaranteed. And we can see here that the maximum didn't happen. It could have happened, but it's not guaranteed. And in our third example, it is on a closed interval, but in this case it is not continuous because we had the removable discontinuity. So again, the max and the min were not guaranteed for this one, and we didn't have a minimum. So next we're going to talk about relative extrema and how they relate to critical numbers. So first off, the definition of a relative extrema, it says if there is an open interval containing c on which f of c is a maximum, then f of c is called a relative maximum of f. So open intervals are going to give us relative maximums. And if there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum of f. So in this case, it turns out that we don't get these endpoint extrema. So it might be valuable because endpoint extrema, okay, don't take into consideration that this keeps on going. So yes, it's an extrema in the fact that we closed our interval off there, but if we think about it in terms of open intervals, like this one right here, we really get an extrema. This is actually a minimum of the function, and we call it a relative minimum. All right, next we want to find the value of the derivative of each function at the relative extrema. So we're going to do a little exploration. What's happening to the derivative when we have maximums or we have minimums? Okay, so here's our maximum, here's our minimum. What's happening to the derivative? Well, let's find our derivative. We'll use the power rule here. Okay, so there's our derivative. If we want to find what's happening at those points, we're just going to substitute our x value. So f prime of 2 is 3 times 2 squared minus 6 times 2. And here we get 0. And then f prime of 0, we get 3 times 0 squared minus 6 times 0, which is, well, 0 again. So that tells us something here about the tangent line. Okay, and if we were to draw our tangent line at this point, it would have a slope of 0. And if we drew our tangent line here, it would also have a slope of 0. Okay, we're going to try another example. We have now f of x equals the absolute value of x. So here's our function, comes here, it hits 0, and then it turns right back up. Now what did we learn about derivatives at sharp turns in a graph? Okay, so here's your minimum at 0, 0, that's a sharp turn in the graph. The derivative at this point, okay, does not exist. And we're going to just abbreviate that with dne from now on. So the derivative does not exist. So what we're trying to get at is what's happening to the derivative at these relative extrema. Well, it looks like we either get a 0 or we get a does not exist for the derivative at that point. And this brings us to our definition of a critical number. So a critical number, we say x equals c is a critical number if f of c exists, so the function exists at that point, and f prime of c equals 0 or does not exist. So the derivative does not exist or is 0 at a critical number c. Now it turns out that tangent lines at critical numbers can be horizontal, vertical, or don't even exist at all. So how does this relate with relative extrema? We say relative extrema occur only at critical numbers. So if a relative maximum or minimum exists at f of c, then we know that c must have been a critical number. However, if c is a critical number, f of c may or may not be a relative maximum or minimum. So the point here is that lots of stuff is happening at critical numbers, one of those things being maximums and minimums. And there could also be a number of other things as well. But we know if it's a max or min, then it must have been at a critical number. So it's going to be important to be able to find critical numbers of functions. And to do this, all we're going to have to do is find the derivative. Okay, and then set it equal to 0. And then check if it does not exist anywhere. Okay, so those are what we're going to be doing here. So first, let's find this derivative. And we get 12x squared plus 10x minus 42 plus 0. So we want to see, let's check does not exist first. Okay, so do we have any x values where we don't get a y value? Well, because it's a polynomial function, this is going to exist on the entire real number line. So the next we want to set this equal to 0. And when we want to say, well, where does it equal 0? What x values? So in this case, we're going to have to solve this, and we're going to probably factor this one. So let's take a 2 out of each of these because they're all even. So we got 6x squared plus 5x minus 21. And now we'll factor this. And a factor that works is going to be 2x and 3x, and then minus 3 and plus 7. Okay, now each of these factors would equal 0. So in this case, x would equal 3 halves. And in this case, x would equal negative 7 thirds. Okay, so these are our critical numbers right here. X equals 3 halves and negative 7 thirds. All right, let's go ahead and try another one here. This one's going to be a little bit more difficult. You can see one function times another function. So that's going to tell me I'm going to be using the product rule. And you also see here the square root of a function, and so the chain rule is also going to be used here. So let's go ahead and find this derivative. And so we get our first function times the derivative of this function. Well, we'll just change that to be to the 1/2. It's a lot easier to deal with. So we get 1/2 times x squared minus 16 to the negative 1/2. Okay, and then using our chain rule, we need times the inside function, so times the derivative of x squared, which is 2x. Okay, and then we also have plus our second function, which is going to be x squared minus 16 to the 1/2 times the derivative of the first function, which is just 4. Okay, now you notice here, again, we have a negative square root, and we also have like bases in x squared minus 16. So we're just going to factor that guy out. So x squared minus 16 to the negative 1/2. And here we're left with 4x plus 1. And then 1/2 times 2x, which is just x. And then on the right side, remember, if we take a negative 1/2 out of this, we're going to go minus a negative 1/2, and so that equals 1. So we're really left with x squared minus 16, and then times 4. And let's go ahead and simplify this now. And we're going to multiply, we're going to distribute here and here. That's a times sign. And then we're going to flip this all underneath. So we get 4x squared plus x plus 4x squared minus 4 times 16 is 40 plus 24, so it's minus 64 right there. Okay, and all this is going to be divided by the square root of x squared minus 16. And if we rewrite this, we get 8x squared plus x minus 64 over the square root of x squared minus 16. Okay, so that was just finding the derivative. That was great fun. Okay, so we're going to find now where the derivative equals 0. And because this is a rational function, it equals 0 where the numerator equals 0. So we're just going to let 0 equal 8x squared plus x minus 64. Now, if you use the quadratic formula, you actually come out with x equals negative 2.89 and x equals 2.76. Okay, now one thing I want to note for you guys here, right here. So we say it's a critical number if f of c exists. So does our function exist at negative 2.89? Okay, well, when we take a look at something like this, the square root of x squared minus 16, remember, this is only going to work when x is greater than or equal to 4 and less than or equal to negative 4. Okay, so you can see here, if we get anywhere between negative 4 and 4, this becomes a negative number, becomes imaginary, and it doesn't work. So because these two values fall in a range that is not here in the domain of our function, they can't be critical numbers. Okay, so you always want to check, are these numbers in the domain of the function? Okay, next we want to check where the derivative does not exist. So a rational function is not going to exist where the denominator equals 0. So what we're going to do is say x squared minus 16 equals 0, and we're going to solve that. So we can square it. X squared minus 16 equals 0, and this becomes x plus 4 and x minus 4. And so you can see here that x is going to equal 4, and x will equal negative 4. Now these numbers, 4 and negative 4, are actually in the domain of this, because if you do 4 squared minus 16, you get 0, and 0 times 0 is 0. And so we're happy with that because it works. So these guys right here, 4 and negative 4, are your critical numbers because they're in the domain and they make the derivative not exist. These two numbers are not in the domain, so they are not critical numbers. All right, let's keep on going. Next, we want to talk about finding actual extrema on a closed interval. So here are the steps to be able to find your extrema. And first thing you have to do is find the critical numbers, just like we did in the last example. And then evaluate f at each critical number, so you're actually finding the points. And then you also have to evaluate f at each endpoint. So we have to check for any endpoint extrema. Now the least of these values is the minimum and the greatest is the maximum on that interval. Okay, so for right here, we have our function x cubed minus 3x on the closed interval, -1 to 2. All right, so the first thing we have to do is find our derivative because we need to find our critical numbers. So f prime of x is going to equal 3x squared minus 3. And to find a critical number, we're going to set that equal to 0. We can factor out a 3 and get rid of that. So it's x squared minus 1. And we know this is x plus 1 times x minus 1. And so here we're going to get x equals -1, x equals 1. Okay, and these are in the domain of our function, and so these are our critical numbers. Now, is there anywhere the derivative does not exist? Well, no, it's just a polynomial, so it's always going to exist. So, as we're finding our extrema now, we're going to go ahead and kind of set up a table of values, and we're going to start with the left endpoint, and then we're going to end with our right endpoints as well. So left endpoint is -1, right endpoint was 2, and we're going to put our critical numbers in between here. So this critical number is -1, and it's the same as the left endpoint. So we're not going to rewrite that. But this critical number is in our interval, so we're going to write our critical number here of 1. Now these become your x values, and we want to find our f of x values, or the y values. So we'll just plug -1 into this function here. So -1 cubed is -1, and then -3 times -1 is actually +3. And so this becomes 2. Here if we plug 1 in, we get 1 cubed minus 3 times 1. So that's 1 minus 3, which is -2. And for our right endpoint, we get 2 cubed minus 3 times 2. So that's 8 minus 6, and that is 2. Now the highest of these numbers is the max, the lowest is the min. So right here, 2 and 2, they tie for the max, and so we're just going to write both of them as being maximums. And the lowest number here, -2, is going to be our minimum. So what this means is we have a minimum at the point 1, -2 from right here. And then we have 2 maximums on our interval, -1, 2, as well as 2, 2. All right, so let's go ahead and graph this on our interval here. See what that would look like. Here's -1, here's +2. So we have the point -1, 2. We have the point let's see, we have 1, -2. And then we have the point 2, 2. Okay, now thinking about this, it is a cubic function, remember? And so cubic functions are kind of going to look like this. So we have this sort of end behavior. And so we can kind of see what's happening here. Our function actually looks like this. Come down, hit the minimum, come back up, and this actually keeps on going. Okay, so looking at this, this one is a relative min, this is a relative min, and this is an endpoint extrema, a relative max right there. So we have our max, and this one's a maximum only because we're talking about the interval, and this one is our relative minimum. All right, let's move on to another example. Here we have 2x minus 3x to the 2/3, and we're on the interval -1 to 3. So again, first step, find your derivative. So this is why it's an application of the derivative, because we're using it to do something else. So this is going to be 2 minus, let's see, 2/3 times -3 is just -2. And then we're left with x, let's see, 2/3 minus 1 is -1/3. So this equals 2 minus 2 over the cube root of x. Okay, so that 1/3 is the cube root right there. So what we want to do is find where this derivative equals 0 or does not exist. Okay, so let's go ahead and solve for this to see where it equals 0. So I'm going to subtract 2 to the other side. So -2 equals -2 over the cube root of x. And now I'm going to actually multiply by the cube root of x on both sides. Okay, so that's going to cancel there. So we have -2 times the cube root of x equals -2. And we'll divide by -2. Cube root of x equals 1. And if we cube both sides, we see that x equals 1. Now 1 is in our domain, and so this is a critical number. Now we also want to check, where does this not exist? Well, because we have a rational function right here, it doesn't exist where the denominator equals 0. So let's go ahead and just set cube root of x equal to 0, and then we can cube both sides. So the derivative does not exist when x equals 0, so this is also a critical number right here. Okay, so as we're testing our graph then, let's make our xy chart, or f of x chart. And we'll start with our left endpoint, which is here at -1. Then we'll move on to our critical numbers. In order, it would be 0, and then 1, and then we'll end with our right endpoint of 3. Okay, so go ahead and find those values right there. We're just going to substitute them in. So if we plug in -1, we get -5. If we plug in 0, we get 0. If we plug in 1, we get -1. And if we plug in 3, we get -0.24. So you can just use a calculator to get those, and here are your values. So looking at this, let's identify what's the minimum value in all of this. Well, -5 is the lowest, so this gives us our minimum at the point -1, -5. And what's the highest value here? Well, the highest value is 0. And so this is going to be our maximum at 0, 0. Okay, so this is the relative min and this is the relative max. So let's go ahead and graph these. We can plot all these points. So -1, -5. And then we have 0, 0 as our maximum. We have a couple other points, 1, -1, and 3, -0.24. Okay, and the way this works, actually, I'll draw this for you. We have a straight line here, and then we have a curve that goes something like this. Now when you look at this, this is the absolute minimum on this interval, and this is the absolute maximum on the interval as well. Alright, let's move on to our final example. And this same idea still applies to all trig functions. And we're going to be on the interval 0 to 2 pi. So first thing we have to do is find our derivative. And with the trig functions, this is going to be 2 cosine x. And then this is going to be minus negative sine, so plus sine of 2x. Oh, and we have a function in here, so let's also use our chain rule times the derivative of 2x, which is 2. So if I rewrite this, I get 2 cosine x plus 2 sine of 2x. Now if we look here, sine of 2x, we're actually going to use our double angle formula here. So sine of 2x really equals 2 sine x cosine x. Okay, so we just changed sine of 2x into 2 sine x cosine x. And we still have this 2 out in front here. As well as the 2 cosine x. Now what that did for us is, because we're going to try to set this equal to 0, we need to be able to factor it. And so this creates a common factor of cosine x. And then we also have a common factor of 2. So we're going to factor out 2 cosine x. And because it's the same as the term here, we put a 1. And then here we're left with 2 sine x. Okay, and we want to see where this equals 0, so we have our two different factors. So it's going to equal 0, where 2 cosine x equals 0, as well as 1 plus 2 sine x. Okay, so solving this one, we can get rid of the 2. So where does cosine x equal 0 on this interval? Well, you got to take a look at your unit circle again. And it turns out that it happens when x equals pi over 2, as well as 3 pi over 2. So again, check out the unit circle and you'll get that. Now, are these values in the domain? Yes, they are. So these are some critical numbers right here. Let's check out this other one. We'll subtract 1 over. So minus 1 equals 2 sine x. Then we'll divide by 2. So negative 1/2 equals sine x. So where does sine x equal negative 1/2? Again, check out that unit circle. It's actually going to happen at 7 pi over 6 and 11 pi over 6. And since these are also in the domain, we call this a critical number. Okay, so now let's go ahead and find our maxes and mins. So we'll just make our XY chart here. Make it a little cleaner for you guys. And we want to start with our left end point. So that's going to be 0. And then we want to move on to our critical number. The next one would be pi over 2. The next one would be actually 7 pi over 6. And then 3 pi over 2. And then 11 pi over 6. And finally, our right endpoint of 2 pi. Okay, so now we just have to plug all of these numbers back in up here. So I'm going to let you try that on your own. Plug in 0, you get negative 1. When you plug in pi over 2, you get 3. When you plug in 7 pi over 6, you get negative 1.5. When you plug in 3 pi over 2, you get negative 1. When you plug in 11 pi over 6, you get negative 1.5. And when you plug in 2 pi, you actually get negative 1. Okay, so looking at this, 3 is going to be my highest, and so this is going to be my maximum here at pi over 2, comma 3. And looking at this, we're actually going to have two mins because negative 1.5 is the smallest. And so our mins are going to be at 7 pi over 6, comma negative 1.5, as well as 11 pi over 6, comma negative 1.5. Alright, so let's go ahead and plot all of our points and show that these are the mins and maxes. So we have 0, negative 1, we have pi over 2, comma 3, we have 7 pi over 6, okay, so that's just going to be a little bit more than pi, and that's going to be here at negative 1.5. And then we have 3 pi over 2, which is at negative 1. Then we have 11 pi over 6, and that's also at negative 1.5. And then we have 2 pi is at negative 1. And so we can kind of join our curve together here. Okay. And so you can see indeed we do have a maximum here, and our minimums are going to be right here. Alright, so that has been our lesson on 3.1 on extrema on an interval. Thanks for watching, and we'll see you in class.